Good afternoon, everyone. It is Monday, the 24th. Just as a reminder, next week on Monday, we do not have class because it is Memorial Day. So I actually need to take a look at the calendar here and see what it is that I put on our syllabus for this spring. So just give me a second. Let me open this up. Okay, right. So next week is going to be our last lecture. Not next week, excuse me. You know what? Hold on a sec. I need to look at the LaGuardia calendar for a moment. All right, so according to the syllabus and LaGuardia's calendar, our last day of lecture is going to be Monday, June 7th. I have our space mission assignments due by June 11th, which is that Friday. Monday, June 14th, is the last day of finals week. During our normal class time, we're going to have the presentations. So make sure that you are there for that. Everyone's expected to be there the whole time. I will have a sign up sheet with times. That way people can make sure that they're signed up for the time that I guess best suits them. And that will be the end of the semester. All right, so let's get started. All right. So just as a reminder, last week we were talking about HR diagrams, those Hertzsprung-Russell diagrams, and we were focusing on stars belonging to the main sequence. These are stars that are fusing hydrogen into helium at their cores. And on the HR diagram, the main sequence makes up this long diagonal segment that runs from the top left to the bottom right. I'll pull it up here for you. This is the main sequence. And we have stars that are very massive and stars that are not very massive at all. Right? There's a large temperature range. So these stars with low mass have lower temperatures. They have lower luminosities, and they have longer lifetimes, right? And they are redder. Up here, those more massive main sequence stars are bluer, have shorter lifespans, are much hotter at their surfaces, and are way more luminous, right? And are bigger in general. All right, so now what we're going to talk about is where do these stars form, or how do these stars form? And it begins with a molecular cloud. These giant accumulations of spread out gas that permeate space. And what happens is these bits of gas, which often we find between stars, right? This is called the interstellar medium, all of this red stuff. Right? These are our molecular clouds. Notice how they tend to be between stars. Right? And when this gas here, when these molecular clouds contract, right, they basically clump into a very dense region of space, and it gets very hot, and it starts to undergo nuclear fusion, and a star is born. And it looks something like this. Right, so you have this big, giant nebula, this large gas cloud. It's not luminous, right? It doesn't give off its own light. And it just starts to pull itself in under its own gravity. And it clumps in a bunch of different regions. It's not like it all necessarily has to clump into one fragment. They can clump into multiple. And each of those fragments then starts to compress and flatten out into a disk. And inside, in the very middle of those, are our protostars. Right? This is like essentially nebular theory, right? How a planetary system is born. Right, so if we look at it in 6 stages, it looks something like this. I want you to pay attention to the scale of distance at the bottom of each image. Right, so we have this dark cloud. You can sort of see that there are 4 regions here that are a little bit darker than the surrounding cloud. These are dense core regions of the cloud. And we're talking about, like, I mean, from one side here to the other, this is 200,000 astronomical units across, which is 200,000 times the distance between the Earth and the sun. And the cloud itself is way larger than that. And it starts to collapse, right? Under its own gravity, it begins to collapse. Something happens that sets it off, you know, where it was once stable, it is now unstable. And it collapses in, and you can see how the scale of our distance here has diminished by about 1,000 or 2,000 times smaller, right? So we're looking at this gravitational collapse beginning. We're going to start our clock here. So this is time 0. Right? All of this gravitational energy is starting to convert into heat and rotational kinetic energy as it starts to spin faster and faster. And it collapses down to a very small size of 500 astronomical units. Right, so again, we're looking at about 2,000 times smaller than the previous image. This takes about 10 to 100,000 years to get from the gravitational collapse to the protostar. So it's not like an overnight process. And as a reminder, you know, we've talked about, or we mentioned in one of our lectures, that looking up at the night sky is very much like looking at a snapshot of a family, because the lifetimes of stars are so vast, changes happen so slowly. You know, big changes tend to happen very slowly. You know, that it takes a long time is my point here. Okay, so we have our protostar. Then the protostar contracts even more into this tiny little central region, right? About, you know, we're going from 500 astronomical units in radius to 100 astronomical units in radius. And so the radius is 5 times smaller. From 100,000 years to 3 million years, we're going from this protostar to our protoplanetary disk, where we have some of our energy, some of the matter being ejected along the poles of the star's rotation. And once that's done, we start to get this nice planetary disk with a bunch of debris, right? You can sort of see maybe the makings of an asteroid belt, maybe some other planets, all right? At this point, we are at a pre-main sequence star. And then about 50 million years after that, we have our young stellar system, where everything is finally settled, right? So we have our fully formed planets here, our fledgling planets orbiting our young star, which is at the center, right? And this is the process by which stars form. So let's break that down now. All right, so we start with the initial cloud. It collapses. It forms a protostar, right? Energy is released. the planets start to form around the protostar. And then once those planets accumulate enough matter, we end up with a planetary system. And again, we can't really watch this happen in real time because, I mean, we can, but it's so slow that like we barely see anything changing. And so scientists use models, computer models, to basically set the initial parameters and say, look, we have this giant blob of mass in space. Here's how much mass we have. Here's what elements it's made of. What would happen to it if we just let the system run? And this model tracks the density of different regions of the mass or of the star. It tracks the temperature at different locations, how much of each different type of chemical element it has, how much ionization or how much free charge there is, and how the size of the star changes with time. And it might look something like this, right? Where you're plotting the abundance of different chemicals at different points in time. So like our star, for example, after about 24 million years might be close to 74% hydrogen, that's the blue, and 26% helium, that's the red, for a total of 100% of its mass. And in about 2 billion years after it's born, maybe a large percentage of that hydrogen has fused into helium, and it's exhausting through its elemental hydrogen, and the helium is building up inside of the star. And then at 3 billion years, we're almost fully out of hydrogen. Right? The star is almost fully helium. Right? So what is that going to do? What does that mean for the lifetimes of these stars? Right? We can't watch this happen in real time. So we're modeling it on a computer, and we're learning about what the star might do once it reaches certain critical points in its lifetime. And for the stars that belong to the main sequence on that diagonal, we have stars that start out relatively low mass, and we have stars that start out with an intermediate mass, and we have stars that start out with a very high mass. And every one of them is going to have a different evolutionary track, right? They're all going to grow up kind of differently. But if we know the initial mass of a star and what it's made of, we can pretty accurately model what the rest of its life is going to look like. And I don't remember if it was last week or the week before, but I recall telling you that the mass of a star is the most important, or is the most defining characteristic of that star. Or the mass of the main sequence star predetermines the rest of its life. And so here are some examples of different stellar evolutionary tracks. Right, and you can just sort of see how like stars that start out on the main sequence with different stellar masses end up taking different journeys through the HR diagram. All right, and again, this is all based on modeling, computer modeling. Right, so we can track a star's predicted change in temperature, or its predicted change in luminosity, or its predicted change in size, etc. So here's an example of how a star like our sun will change throughout its life. Right? That it will grow, it will grow in size, it will get hotter, it will become more luminous, and then it starts to cool off and cool off and cool off. Meanwhile, it's getting bigger and it's getting more luminous. Right, and so we're going to go now and delve into the next stages of a star. So we talked about something called the proton-proton chain reaction. We said that the proton-proton chain reaction is the main mechanism by which main sequence stars fuse hydrogen into helium in their cores. But what happens when the core of a star no longer has hydrogen in it? What happens when the core of a star is just a bunch of helium, right? If the hydrogen's fusing into helium at the core, then that helium starts to build up, and over time, it makes up the core, and hydrogen is like a giant shell around it, right? Almost like a jawbreaker snack. You know, like you cut it in half, you can see all the different layers around it. So this process by which hydrogen fuses to helium is a little different. Excuse me. The process by which hydrogen fuses to helium is a little bit different than this process, in which helium fuses into carbon. It takes 3 helium atoms or nuclei to fuse into 1 carbon nucleus. All right, and this process, just like the proton-proton chain reaction, releases energy, right, proportional to a certain amount of mass that is converted. Right, but this doesn't happen right away. And I'll talk about what that process looks like in a little bit. All right, so where are we? Let's let Audrey into our meeting. Okay. So we have hydrogen that fuses to helium. Helium builds up in the core. Eventually, that helium fuses into carbon, so that energy is continuing to be generated that can sustain the star. Right. This is called the triple alpha process. The reason it has this name is that a helium atom is called an alpha particle. And we need 3 of them to fuse into 1 carbon atom. So it's the triple alpha process. All right. Again, I'll break down that transition in a little bit. So the helium flash looks something like this. Actually, you know what? I'm going to pause for a second. I need to draw this picture for you. Let me just switch over to my iPad for a moment. Okay, here we go. All right. So we have a star that is pretty much all hydrogen. All right, let's just say that we start out with a star. It's all hydrogen. At the core of the star, right in the center, right in the core there, it is very hot. There is a lot of pressure from the outer layers pushing inward. All right, so this is just the star. Is very hot. With very high pressure and with very high pressure at the core due to the gravitational force from the upper layers. All right. The core then starts to undergo nuclear fusion, right? This core is starting to convert hydrogen into helium. So we have lots of fusion happening in that core, and this sort of orange color represents hydrogen. Okay, then our core starts to build up all this helium. But the helium is inert. It is an inert helium core, right? Inert means that there's no nuclear fusion. It's just sitting there, right? It's not doing anything. So we have all of this hydrogen sitting around this inert helium core. All right. And hydrogen is fusing in this like little shell. Right? There's a tiny little shell around here, which still has hydrogen fusion. But the fusion of hydrogen to helium is no longer happening in the core. It's happening in this little shell around the core. So what's happening here? Well, first of all, why doesn't the helium also just start fusing right then and there into carbon by the triple alpha process that was on the screen a moment ago? Well, the core isn't hot enough for helium to fuse into carbon. All right, so the core starts to contract. Core begins to contract, right? Because it no longer has the ability to really push as much on the outer layers, right? The gravity starts to win, right? So the core starts to contract, but in doing so, the helium core is getting hotter. Not hot enough for fusion to begin, but it's getting hotter. And that's keeping this layer, this shell of hydrogen, right, around that inert helium core, well heated. And so hydrogen fusion starts to happen really rapidly here because the temperatures get so high, right? And the energy from this hydrogen fusion, goes outward. It tries to escape. Right? And in this process, the star begins to get bigger. The star begins to get bigger. It is glowing brighter because a lot of energy is being released. But as it's getting bigger, it is also getting cooler at the surface. Like when you have a steam in or maybe you have a pot of water and you're boiling it with a lid on, and then you take the lid off and the steam expands while simultaneously cooling off. That's kind of what's happening here, is that the star's outer layers of hydrogen are expanding while simultaneously cooling down. And so the star gets bigger and it starts to get redder. Meanwhile, the core is continuing to collapse, right? That core continues to collapse and collapse and collapse. And eventually, this is where I switch back to my slides. Eventually, that inert helium core starts to undergo nuclear fusion, right? It gets hot enough. And we call this process the helium flash, right? So suddenly it just gets hot enough for helium to begin fusing into carbon. And as soon as that happens, the core gets extremely hot and the entire helium core basically at once begins to fuse helium into carbon, right? And the it just gets so hot, and the core then starts to push out, and the core expands. And as soon as the core expands due to this added, like all this crazy amount of heat, it actually starts to cool the core down a little bit. Right? I don't know if that makes much sense to everyone. Are there any questions on that? Right, so there's this inert helium. The helium gets just hot enough for fusion to begin into carbon. And with that, the helium core begins to expand, right? And as it expands, because it's getting so hot, it starts to cool down. All right, so you could have a star that becomes a red giant as it's growing that inert helium core. As soon as the helium flash happens, the red giant can shrink and become less luminous. So let's see here. Give me a moment, give me a moment, give me a moment. Okay. So what happens next? Well, eventually, the same thing that happened to helium, from hydrogen to helium, where that helium just sort of builds up in the core, right? The helium, you have this inert helium that builds up with a shell of hydrogen fusing around it. Once the helium core starts to ignite and begins to fuse into carbon, then you start to get carbon building up at the core. Right? And eventually you end up with this giant ball of inert carbon surrounded by a shell of helium in which it's fusing helium into carbon. And that is surrounded by another shell of hydrogen that's fusing into helium. So it's like it's really starting to look like one of those jawbreaker candies. Right? Now, for a low mass main sequence star like our sun, there's never ever a point where this process, this double shell fusion, reaches an equilibrium, and eventually the star is going to die a fiery death. The star will explode as it gets really hot. It starts to send a lot of energy periodically in pulses up to the surface, and at some point, that double shell around the carbon core just gets ejected into space, right? This process is this process leads to what's called a planetary nebula. You might recognize this one. This is the Cat's Eye Nebula. And if you look right at the center there, there's a little white dot right where my mouse is. Right? This is the core that's left over from this star. And you can see the red around it. This is our hydrogen. The blue in here, that's our helium. Right? They have different colors. And we have this white dwarf, this giant core of carbon that is incredibly hot and is glowing. It's not undergoing any nuclear fusion. Right? And so you might wonder, well, if it's not, don't stars need fusion to support themselves? right? Isn't that how they sort of keep themselves alive while gravity is trying to crush the star? And what happens here is after these double shell stars eject their outer layers, this white dwarf is basically this just giant mass of carbon that is holding itself up with its own electrons, right? It's like it's being compressed so much that its electrons are actually supporting it and preventing it from collapsing any further. And it doesn't need nuclear fusion to do that. All right, so at the end of the fusion process, right, basically the star can't get hot enough to start to fuse carbon into something else. And so that's the end of its life, right? Once it can no longer fuse into heavier elements to support itself, the star dies. Right, so a white dwarf, again, is this giant ball of inert carbon that's just sitting in space. Anybody know what happens to carbon when you put it under a lot of pressure? You could type it into the chat if you know. When carbon undergoes a lot of pressure, what does it turn into? Or what does it make? Yeah, diamonds, right? And so a white dwarf is under so much pressure, it is believed that they have diamonds, the giant diamond cores, giant diamonds floating through space. Right, so it looks something kind of like this. Right, so here's our sun. All right, it is on the main sequence in this bottom image, meaning it's just fusing hydrogen into helium. Right, so hydrogen fusion at the core. Then it starts to grow into this subgiant. Right, we have an inert helium core. Right, this helium isn't doing anything, it's just sitting there. Then you have the hydrogen fusion happening in a shell, right? And it starts to expand as the core contracts, right? If you're following my mouse, right, the sun leaves the main sequence, becomes a subgiant, grows, 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 and then right around here, we have the helium flash. The helium flash where the core cools down a bit, the surface gets hot still, and the luminosity decreases, and the core, that inert helium core, begins to undergo nuclear fusion. So now we have helium fusion happening in the core and hydrogen fusion happening in a shell around it. And that star is going to get cooler, and it's going to grow to be more luminous, and it'll become a red giant. And by the time it's a red giant, it has this inert carbon core with helium fusion happening in one shell around it, with hydrogen fusion happening in another shell around it. And then eventually, it's not, because it's not stable, it'll never reach stability here. It, through a series of thermal pulses, ejects its outer layers. And that forms a planetary nebula. And what's left behind is a white dwarf. And over time, because the white dwarf will never start to undergo fusion again, it'll just get cooler and cooler and cooler and become a brown dwarf. Okay? Eventually, it'll lose all of its heat, right? And it won't glow. So to summarize, a little bit about what we've talked about, the life stages of a low mass star. First, you have that hydrogen fusion happening in the core, right, which makes it a main sequence star. So it's all stars begin on the main sequence, right? Then you end up with hydrogen fusion happening in that shell around, the inert helium core, which is contracting. It's getting hotter and hotter and hotter and driving this hydrogen fusion in the shell, right? Then it gets hot enough that helium fusion begins in the core. That is after the helium flash. And then we have double shell fusion, where the helium fusion in the core starts to leave behind this inert carbon, which has a shell of helium fusion around it with a shell of hydrogen fusion around that. So how do these stars die? Well, eventually the hydrogen and helium are ejected and you are left with that giant mass of inert carbon, which we call a white dwarf. Again, just looking at some pictures here. Oh, excuse me. Sorry, this is a high mass star. So a high mass star is kind of similar, right? Take a look here. You start out with a mass of about 25 times the mass of our sun. Right, so this is a very, very large star. It's a protostar. By the time it becomes a fully fledged main sequence star, it'll be a blue color. It'll be very high temperature. Right? Let a couple of billion years pass, and this blue main sequence star grows to become a red supergiant. It cools so much that it goes from blue to red. All right. Eventually, it'll undergo helium core fusion. Right. The star will get really hot again. It'll become nice and blue at the surface, right? Or maybe perhaps white, depending on your perception of color. All right. And then it'll just start to fuse heavier and heavier elements. So it can go well beyond the fusion of carbon. It can start to fuse heavier elements like nitrogen and neon and oxygen and so on and so forth. And when these stars die, it's way more cataclysmic of a death. These stars are so massive. I mean, they have so much more mass that when they die, they basically can't sustain themselves under their own gravity anymore. So they don't just explode outward because of a series of thermal energy pulses. What happens is they get so big and then fusion at the core stops and gravity starts to win and the star contracts and contracts and contracts. And it basically smacks into itself and then rebounds outward. And that process is called a supernova. And when a supernova occurs, what's left behind is one of two things, depending on how much mass the star had. Either a neutron star will be left behind, which is basically a cluster of neutrons, not even the nuclei of atoms, just neutrons, or a black hole. It is possible that it could bend space so much, contract so much material into a very dense region of space that it becomes a black hole and warps the fabric of space-time incredibly, rather extremely. All right, so the life stage of a high mass star is very similar to that of a low mass star, but it's got an extra couple of steps. Right, so this is pretty much the same, right? All the way down to the helium core fusion. But the carbon here, because of how much extra mass there is in the outer layers, the carbon at the core can get hot enough to start fusion. And the core of a supergiant star, which if you look at like the size of this star compared to the size of its core, right? You can see that we're talking about very, very vastly different size scales. We get much heavier elements. We get hydrogen, helium, carbon, neon, oxygen, silicon, and iron. But iron is the dead end for these supergiants. Iron is the dead end. Once a star begins to build up iron, inert iron in its core, the star is basically on its last legs. Because iron will never, ever fuse into a heavier element to release energy. So why is that? Why do stars die with iron? Well, what are we looking at here? We're looking at a graph that's plotting the atomic mass of our particles. So this is basically like going from left to right on the periodic table. Hydrogen is number 1, helium is number 2, carbon is number 6, so on and so forth. Right? Iron is the what the heck do I have here? Right, iron's got a oh my god, well, now I'm blanking. Sorry, it's late in the day. If you couldn't tell, I'm yawning a lot right now. Right, iron's atomic number is 26. Right. Oh no, I see it here. That doesn't make sense to me. Hold on, why does it say that? The atomic mass here should be 52. It just looks so much closer to 60. It's throwing me off here. All right, so this iron, maybe this should be a little bit further to the left. In any case, on the y-axis, we're looking at the mass per nuclear particle. Hydrogen atoms have more energy per mass than hold on a sec. Hydrogen atoms have more energy per mass, or excuse me, more mass per particle than helium. So when hydrogen fuses to helium, some of that energy can be transformed into light, or rather some of that mass can be transformed into light and thermal energy. Okay, hold on, let me back up. I just got in the groove with my own mental happenings. That took me a second. Okay, so if you take one hydrogen atom, right, and you compare it to a helium atom, or if you're looking at like 4 hydrogen atoms for every 1 helium atom, the 4 hydrogen atoms that make up, that will eventually convert into the helium, have more mass, right? So that when these 4 hydrogen fuse into helium, energy, some of that mass can be converted into energy, and that sustains the star. The same thing happens when helium is converted to carbon, right? So we need 3 helium atoms to make 1 carbon atom, okay? The 3 helium atoms combined have more mass than 1 carbon atom. So when the 3 helium atoms fuse into carbon, some of that mass gets converted to energy. That supports the star. That process keeps happening until you get to iron, okay? Once you get to iron, to fuse iron into the next heaviest element actually requires you to add energy into that reaction to make it happen. So from hydrogen all the way up to iron, the process of fusion releases energy. Energy is a byproduct of that reaction. But once you try to start fusing iron into things that are heavier, energy is actually an ingredient for that reaction, right? It is one of the necessary, or it is one of the requirements to make that reaction happen. So a star isn't going to fuse iron into something heavier, because that defeats the purpose of the nuclear fusion, right? The purpose of the fusion in a star is to release energy so the star can support itself. If once you get to iron, fusion no longer releases energy, then the star is not gonna fuse it into anything, right? The star doesn't give up its energy to fuse iron into something heavier. Now, here on Earth, you know, we talk about nuclear energy, right? And nuclear power plants. Our energy comes from the fission of nuclei. So like when you take uranium and you fuse and you fission it into lead, as you can see here on the right side, uranium into lead. Lead has a lower mass per nuclear particle than uranium does. So when uranium undergoes fission, this process releases energy, right? And lead, and plutonium into something else releases energy, so on and so forth. And so there are so fusion and fission can both release energy, but iron is the lowest point on this chart. Right? Once you get to iron, you have to add energy if you want to undergo nuclear fusion, and you would also need to add energy if you wanted to undergo nuclear fission. All right, so iron's the bottom of the curve here, right? Okay, and this is basically what I said a moment ago. Right, so these high mass stars end their lives with this giant supernova, this giant cataclysmic explosion, right? And there are two types of supernova. There's the kind that we just discussed, where a large high mass star collapses under its own gravity. And then there's another kind. So the kind that we're talking about just now with that cataclysmic explosion, star collapses under its own gravity and it rebounds outward. That's called a type 2 supernova. We're also going to briefly discuss a type 1A supernova. So consider a binary star system. So you can have a white dwarf and a red giant here. The white dwarf can pull some of the material off the surface of the red giant, and you get this like accretion disk around it, right? And as the accretion disk starts to build up and material starts to accumulate and it spins faster and faster, the pressure, and the temperature are increasing on that inert white dwarf, that inert carbon sphere floating through space. And eventually, from this accretion of the material from the red giant, that white dwarf can get hot enough to spark the fusion of carbon. And when that happens, the white dwarf will explode in a supernova. And this is a different kind of supernova than when the core of a massive star collapses, right? But it is still called a supernova. And so this is the one that we were looking at a moment ago. This is the remnant of a type 2 supernova. This is called the Crab Nebula. And we talked about nebulas before, right? That's like bringing us back to nebular theory, where we were talking about how a planetary system forms from a collapsing gas cloud, right? From a nebula, right? Which is Latin for cloud. So all of the nebula that we talked about earlier are leftover supernova. They're basically leftover stars that exploded. And this starts a process of stellar rebirth, right? That a star lives its life, it dies, it explodes, and then the remnants, what's left over from that explosion, actually form new stars. Right, supernovas release a lot of energy. We're able to study supernovas while there are a lot of things that happen in the universe that take a long time, right? When a supernova happens, it only lasts a little while. And so there are some processes that we can see happen throughout the universe. This is an example of a supernova from 1987. You can see the before and after of the supernova. This is a long exposure shot, which is why it appears so much brighter. I mean, you can see that everything appears brighter, but this supernova appears really bright. And it only lasts for a couple of months. All right, so let's summarize the role of mass in a star's lifetime. Right? That, like I said, and I can't stress this enough, the mass of a star determines the rest of its life. We've talked about how stars with high masses live short lives. They get very big, hot, they can fuse up to iron in their core, and then they have these giant supernova explosions. Low mass stars don't ever get hot enough to fuse that carbon, and so eventually they eject their outer shells and leave behind a white dwarf. But they live much longer lives because they don't burn through their nuclear fusion. They don't burn through their nuclear fuel as quickly. Low mass stars. Again, this is just a reiteration of earlier. Right. We have our protostar, yellow or red main sequence star, red subgiant, helium core fusion, right? Then eventually it can become a red giant or supergiant again, and we get that planetary nebula, that explosion, and then what's left behind is the white dwarf, right? Then we have our high mass stars. Same stuff, except instead of having double shell fusion, you have multiple shell fusion, right? Where you have multiple shells. And these are so much more massive that when they die, they collapse in on themselves and give up, explode in this violent supernova. All right, so here's our summary. And just sort of touching on all of the bits and pieces here. Right, I don't want to reiterate too much because I feel like I'm just repeating myself at this point. But this is where we're going to stop for tonight. All right, so it's been about an hour. I'll stick around if anybody has any questions. All right. If you'd like, you can head out. Again, if you have questions, you can stay. I'm going to stop the recording now. All right, so take care, everybody that's watching. Have a good day, good evening, whenever it is that you're watching this.